Hello everyone, we will start with the basics of rheometry. The word of course rheometry is slightly different from what we hear in terms of rheology. So, the terminology which I use generally for rheometry is basically how to use a rheometer to generate good rheology data and how we can really make effective measurements using a rheometer. So, that is what I define rheometry as, and rheology in general is investigating bulk properties of materials by measuring viscosity, modulus and many such related parameters to investigate the properties of the material with respect to different parameters. The parameters can be based on the flow of that material, or it can be also based on the deformation of the material, or it can be a combination of both these two. And we are basically going to characterize these materials in terms of their flow and deformation behavior. Okay. So, that is basically when we discuss about rheology, it is a data which we are producing and then inferring the materials property based on this particular data that we have produced by measuring on a rheometer. So, let us take a short look at the complete spectrum of material that we are going to measure using rheology. So, if you see on the left side of the road, you have very low viscosity materials, or I would say these are ideal Newtonian materials. So, these materials are very simple structures, fluids like water, solvents, and on the right side you can see materials which are absolutely solid like steel at room temperature, for example, would be a perfect solid. But in between you see lot of different type of materials. These materials are actually a mixture of viscous as well as elastic part. So, as you move from the left side of the rheology road towards the right side, you will see that the materials become more and more complex, because if you take a pure viscous material, it is easy to characterize that material by simply measuring viscosity, and we can say that the viscosity of these materials will be constant irrespective of how we are deforming or flowing them. And of course, the only thing that changes the viscosity of this Newtonian material is basically the temperature, okay, and to a certain extent pressure, but temperature would be the main criteria. But as we move towards viscoelastic materials, as we have both the properties inside that material, then the materials are more complex to measure, because they will have different viscosities at different deformations, and that is what we have to really measure. And when we move to what we call as viscoelastic liquids towards viscoelastic solids, okay, there of course we cannot characterize the materials simply by steady shear measurements. Okay. So, from viscoelastic from viscous material to viscoelastic liquids, okay, you can easily do measurements by rotational measurements itself. So, it is a steady shear measurement as we call it. But when we move from a viscoelastic liquid to a viscoelastic solid, we no longer can really measure it with just simple steady shear. In that case, we have to apply a different technique, which is basically called as dynamic oscillatory measurements. Okay. From that only we can really measure both these properties, the viscous properties and the elastic properties. The reason is, if you are trying to apply a steady shear material to a viscoelastic solid, okay, you generally will break the structure, and the steady shear measurement would always go into what we call as a non-linear region of measurement of these materials. Okay. But we want to have both the information, the linear in the linear region, how these materials are behaving, and what is happening of course also in the non-linear behavior. So, if you see on the bottom of this slide, you have the rotation and oscillation. So, oscillation measurements can be done for any type of material, okay, whether it is a viscous material, viscoelastic liquid, viscoelastic solid, or even a solid. But if you take rotational measurement, it is limited to, I would say, viscous materials, pure viscous materials, and viscoelastic liquids, and maybe very I would say very soft viscoelastic solids also, but a very small part of that, not the full range, because if the elasticity is more, when I say elasticity more, I will explain you in more detail how I can define and say elasticity more, but for those materials it is just impossible to do a rotational measurement. Okay. And at the bottom of that you see different type of geometries that are usually used for measuring these on a rheometer. So, you have if you take very low viscous materials, then of course you require larger surface area of interactions. So, for that you will require coaxial cylinder geometries, and then as you move towards more stronger structures, okay, then you will require smaller surface areas. So, you move towards from coaxial cylinder systems to plates or cone plates, and this cone plate sizes also become smaller and smaller when you go towards from a viscoelastic liquids to a viscoelastic solids. So, maybe during a viscoelastic liquid measurements you may require a 50 mm geometry, but for a viscoelastic solids you will require a 25 mm geometry. And further down, like if you go to very strong solids like say thermosets, you are doing a curing experiments, then generally we use PP parallel plate geometries like 12 mm, 8 mm type of geometries. So, they become smaller in size because the interaction required in this interaction that we measure in these small surface areas are sufficient to characterize and get the required information. So, what we are doing is basically we are applying in the measurement to the sample either a stress and measuring strain, or applying a strain and measuring stress. Okay. So, if you look at the two plate model, what is important is in this measurement is you should have a defined gap between the two surfaces. The sample is basically getting sheared between these two surfaces. In general, these two surfaces are parallel, okay, and they are one of the surface is in a standard condition is stationary, and one of the other surface is moving. Okay. So, when we are giving a deformation, okay, we define the strain, which is nothing but the displacement divided by the gap between these two surfaces, and the velocity divided by the gap will be the shear rate. So, the strain is the deflection angle or the displacement divided by the gap, and the shear rate is nothing but the velocity divided by the gap. Okay. The stress induced due to the application of the shear rate or the shear stress is nothing but the torque which is experienced by the sample. Okay. So, when I am moving this upper plate with a certain displacement or with a certain speed, so I require certain amount of torque, okay, to get that defined displacement or defined speed. So, that torque which is measured, okay, multiplied by the divided by the surface area, would give you the stress value. So, the torque divided by the surface area is your stress, okay, and your velocity by gap and displacement by gap will give you the shear stress or the shear strain respectively. So, this is what we see, shear stress divided by shear rate and your displacement by gap, and of course, this is how basically the measurements are going to take place on a rheometer. So, in the rheometer you can apply either the shear stress and measure the shear strain, or you can apply the shear strain and measure the shear stress. So, how does the rheometer does this? Okay. So, if you look at the hardware of a rheometer will have a motor, okay, and this motor is going to apply either the stress or the strain. So, in the motor basically you will have a coil which is basically given a current, okay, and because of the current basically the rotor, which is generally a magnetic rotor, will rotate. Okay. So, you generate a sort of drive inside the motor using the current. Okay. Now, there can be different type of motors also, okay, but let me take an example of a very simple direct current motor. Okay. A direct current motor will have multiple coils. So, it will have for example 12 coils, and similarly in the rotor it will have 12 magnets. Okay. So, this 12 coils basically you can make this 12 coils in such a way that you can become north south, north south, north south, north south. So, you keep on giving currents in such a way that you are actually in a way rotating, making a rotating magnet. So, you are making these coils magnetic field rotate. Now, since this coil's magnetic field is rotating, the magnets on the rotor which is on the center shaft, okay, so it is not connected mechanically to it. So, this rotor is actually floating in air on what we call as an air bearing. Okay. The reason, of course, we will not like to have a bearing like an air bearing, because we want to have almost zero friction. Okay. So, we cannot have absolutely zero friction, we will have some friction caused by the air, but this air friction is so low that we can easily get information of very, very small structures. The reason we want to have low frequency friction is because we want to measure very small torques. Okay. And to measure these small torques we should not have any friction in the air bearing. So, this whole shaft with this rotor having these magnets is floating in the air, and this outside coils are making this magnetic field move. Okay. And so, this rotor which also had the magnets, so the rotor south will actually follow the north which is actually rotating. Okay. And similarly the rotors south will actually the rotors north will actually align with the south of the moving coils. Okay. So, it is actually synchronizing with this what we call as the rotating flux which is generated in this motor, and that is how we can control small positions. Okay. If I want to control positions which are like into nano radians, I can apply only that much amount of current to generate a very small flux to have that small movement. Okay. So, you control position. Okay. So, your deflection angle is controlled, your deflection angle divided by the gap of the geometry is going to give us the strain. So, you can control the strain, or the speed at which you are changing the position can be also controlled. So, the speed is your velocity divided by the gap, your shear rate can be controlled. Okay. And now, since you know how much amount of current you are giving, so that is equivalent to the torque. Okay. So, this is also being measured. Okay. You basically miserly give the current to really control these movements and control the speed, and you keep on measuring also this current. Okay. And that is equivalent to the torque which is basically getting induced into the sample. So, we measure the torque, we measure the speed and the position, and from that calculate the stress, the shear rate and the strain. Okay. And then use this into our equations to measure this. Of course, we are measuring each and every point of application. So, we can measure a steady shear, or we can measure an oscillation. Okay. And of course, when we have the oscillation, we are also going to use these vectors of oscillation to measure what is the phase angle between this the actual strain that we are applying and the torque signal that we are getting, which is also an oscillatory. So, the torque vector is basically also used to measure the phase difference between the stress and the strain signal. So, when I say stress signal, it is actually a torque signal. Okay. And when I say a strain signal, it is actually a position signal. Okay. So, the position is converted to strain and your torque is converted to stress. Okay. Below, so on this motor, of course, you will have a coupling, and to this coupling we can have different type of geometries. Okay. The geometries will define actually the surface areas and the gap, okay, and those are also actually used in this equation of converting the torque to stress and the position to strain. Okay. And at the bottom we will have different type of temperature controls, okay, and these temperature controls will be used to control the temperature of the sample, and the temperature controls can be of different types also. You can have a very simple one, what you see on the screen, which is just a flat plate. Below that you have either heaters or you have electronic Peltier elements to either heat or cool, or you can have actually ovens which are actually going to come and close around the sample, okay, or you can have a flat plate and a hood on the top of it. So, there can be variety depending on what type of samples you are going to measure. If your samples are going to be very big, then you will, so if your samples are very big, then you would require bigger temperature devices, and if your samples are very small, like you measure between two parallel plates or Conan plates, then you require very small simple flat plates that we saw in the earlier scheme would be good enough. It is just a cross section of the motor that you see. If you see this part over here is your air bearing. So, that is where your air is flowing inside and making this whole shaft float into the air, okay. And the bearing basically is in two parts. This bearing over here is your radial air bearing, and the bearing below over here is your axial air bearing, because we also want to make sure your shaft remains absolutely perpendicular, does not wobble at all, okay. So, that axial air bearing holds the shaft exactly straight, okay, and the radial air bearing makes it float and rotate on the axis without any, or I would say minimal friction over there. And this is your motor, and on top of that you have your optical encoder, and this encoder is actually measuring the position, okay. So, this is the basic hardware of the motor, and these are the different measuring geometries. So, in general the parallel plate, Conan plate are the most common measuring geometries used, because they are easy to load, easy to clean and can measure a lot of spectrum of material, starting from, I would say, viscous material to viscoelastic solids can be taken care by just the parallel plates and Conan plates. For very low viscous materials, you may have to go to higher surface area like the concentric cylinders as you see over here, okay. And then of course, if you go to very stiff materials like solid bars, okay, in that case of course we cannot use either the Conan plate, parallel plate, or even the coaxial cylinder systems. Then you will have to use different geometries like what you see on the right side over here. These are solid fixtures or solid clamps, okay. So, this material will be then clamped between these two geometries, and you will apply the oscillation across the cross section of either a sample which is a cylindrical sample or a sample which is a rectangular solid, okay, a prismoid. There are other relative measuring geometries possible, okay, depending on again the samples. If you have samples with very large particles, for example slurries, cements, mortars, marmalade, with big fruit pieces, something like that, then you cannot do it with the small gap geometries like Conan plate or coaxial cylinder systems, okay. Then you have to go to larger gaps, okay. So, these are the geometries which are going to be used like vanes or steerers for such type of sample matrices. But when you go to such geometries, these are not going to give us absolute values of viscosity and moduli, okay, because the standard DIN equations for defining the proper shear stress and the proper shear rate will not apply to very large gaps, okay. So, you can get an approximation of that, you can calibrate these geometries to get absolute values here. So, to choose a proper measuring geometry for your samples, you can just look at the surface area of geometries as the main parameter, okay. If you have samples which are very weak, very thin, very structures like foams for example, okay, very, so they are the structural strength of this material is very weak. So, for that of course to get a response out of this material you require larger surface area of interaction. So, in that case you can use coaxial cylinder systems. The coaxial cylinder systems will give us the largest surface area of interactions. Again the coaxial cylinder systems can be a single gap or a double gap over here. Double gap will increase the surface area even further. So, if you measure very small viscosities and you want to measure at very small strains, okay, then you would definitely require a double gap. But if you are going to measure lower viscosities at medium shears or good enough strain values, then you can also do it with a single gap. For example, if I want to measure water at a shear rate of 1 or 0.1, it would be impossible to measure with a single gap coaxial cylinder system, then you would require to have a double gap. But if I want to measure with water at a shear rate of 50 or 30, okay, no problem, that can be done with a single gap. Okay. So, it is just a matter of the structural strength and of course, the matter of what is the deformation. If you want to measure at very low deformations, then of course, you require even larger surface areas. So, it is we call the coaxial cylinder system as a specialist for liquids. You have the cone and plate, which is, I would say, one of the best geometries which can measure from low viscosities to medium high viscosities, most versatile geometry, I would say. It has a lot of advantages because it has a shear distribution across the surface which is constant from center to the edge. Okay. So, it is very good for it is a good accurate measurement of viscosity using a cone and plate. Okay. So, it is like it is very similar to the coaxial cylinder system, but coaxial cylinder system will require a larger amount of samples and they are also difficult to clean. Okay. But cone and plate, the sample volumes are smaller and they are very easy to clean, the sample loading is also very easy. Okay. The only disadvantage in the cone and plate is that if you have samples with big particles, then it is not possible to measure. The reason being, if you see a cone, ideally a cone would have a very sharp tip at the center and the tip would actually touch the bottom plate. Okay. But if you manufacture that cone in that way and the tip is touching, then we will start measuring the friction between this touching point of the cone to the plate. Okay. So, what we do is we trim off this tip, okay, and whatever we trim off, that is measured, okay, and that will become our gap. Okay. And now, this is very important that we maintain this gap. Okay. If this gap, let us say I have trimmed off 50 micron or 100 micron, okay, then I have to maintain that gap, so that virtually that cone, when it gets completed, it is still touching. Okay. So, that is why this maintenance of gap is very important. Now, but if I am going to do a temperature sweep, for example, in that case my gap is actually changing physically, because there is going to be expansion. These are made of metals. So, the small expansions also are going to contribute to a very large error in a cone and plate. So, that is also the reason why in a cone and plate we cannot do a temperature sweep. You can only measure at isothermal conditions. So, if you are measuring at 50 degrees, so you do the 0 gap and you set the gap at that 50 degrees and measure at 50 degrees, that is it. You cannot then change from 50 degrees to 40 degrees without doing a 0 gap again. Okay. So, it is very important in a cone and plate to measure at isothermal conditions only. Okay. And you cannot measure with larger particles, because these particles can come at the tip, can get trapped at this small gap, and then you are actually measuring only those small amount of particles which are trapped over there, and you get problems. So, it is, I would say, not the best geometry for measuring slurries or dispersions with large particles. For homogeneous fluids, it is best. Okay. No problem at all. Okay. So, it is one of the most preferred choice of measurement, and you can have so many variety of geometries. If you want to measure very thin fluids, you can have a small angle. If you have very strong structures, you can measure with cone with larger angles. You can have different diameters, different angles. So, variety of combinations of cone and plates can be possible to suit any type of a very wide variety of material, I would say. The other geometry besides this is the parallel plate. Okay, it is one of the most adaptable geometry after cone and plate, and the main advantage I would say for the parallel plate is easy sample loading, and of course we can do temperature sweeps. Okay. Here we can do temperature sweeps because even if the gap is changing, okay, we can measure at any gap, we can actually use that gap calculator. Let us say we start with 1 mm gap. Okay. Now as the temperature is changing, let us say if the temperature is increasing, then the expansion is happening, so the gap is actually becoming smaller. We already can track that by knowing the material. We know, okay, what is the coefficient expansion of that material, and based on that we can know, okay, how much amount of gap is getting lowered and lowered. Okay. And so that is actually used for calculations. Okay. And that correction is made very easily with that. That correction cannot be done with a cone and plate. Okay. But with a parallel plate, it is very easy to do a temperature sweep, and also since parallel plate can be done at variety of gaps, you can use 1 mm gap, you can use 0.5 mm gap, you can use 0.25 mm gap. Okay. So the changeable gap basically also allows you to accommodate different type of samples. If you have samples of, say, which have particles as big as say 10 micron, then I can easily go to 10 times of that gap, which is 100 micron, and so on. So I can actually adjust the gap based on the maximum particle sizes which are present in the sample. In a cone I do not have that option, I have to work at a fixed gap which is equal to the truncation that I have done on that cone. Okay. So but in a parallel plate, because of the variable gap, okay, you are able to also accommodate samples like dispersions, slurries with larger particles, and of course it has the biggest advantage of doing a temperature sweep. So for a temperature dependent experiment, the parallel plate is really best. Of course you can do a temperature dependent experiment also on a coaxial cylinder system, because that is also free of any artifacts which are caused due to the temperature, but the mass of the coaxial cylinder system is so big, because the volumes are so big over there, it is not the preferred, because it takes long time for the sample to get the temperature that you are giving over there. But parallel plate sample amounts are very small, typically 0.5 to 1 ml is the sample volumes of most of the parallel plate geometries, and to heat or cool such type of sample mass is very simple, especially if you are working at a gap of 1 mm and below, then even a very bad insulator of heat can be easily have a very good temperature control. So you can really do a very decent temperature sweep, temperature dependent experiment using the parallel plates. Then of course there are measuring systems for solids, which I told you that they are simple clamps, okay, and these clamps can be of variety of type. You can have solid rectangular fixtures for rectangular samples, you can have circular fixtures for cylindrical samples, and you can also have holders for films and fibers also. So these are something like this over here. Okay. The most popular one are the solid rectangular fixtures, okay, which are used for variety of solid samples, polymer composites, or asphalts, reinforced materials, laminates, and so on. And then of course you have this whole gambit of relative measuring systems, which are used for measuring very difficult samples, like large particle slurries, cement, mortars, concretes. Okay. So you have cylinders which are profiled, or you have vein geometries, you have helical geometries, or you can have ball measuring systems. Many of these use the typical Dinh equation or modified Dinh equations for calculations, and many of them use a different set of calculation, like there is a ball measuring system which you see over here, which basically uses the Mueller-Tyrek equation, okay, for doing the measurement. So, it has to be back calculated in terms of the CSS and the CSR factors for measuring the viscosity and modulus.